Hello everyone, and welcome to our last module in this course. In this last module, I'm going to talk with you about something called non-parametric tests. It's kind of a shift away from what we've been doing. I find them easier to understand than anything. I hope that's good news to you. So in this first video, we're going to review parametric tests. What are parametric tests? We're talking about non-parametric this week, but let's figure out what parametric means. So we're going to talk about types of parametric tests and some of the assumptions of parametric tests. So again, we've come a long way in this course. We started off talking about descriptive statistics. We were just describing data sets. We did this through numbers like central tendency, mean, median, and mode, and dispersion, standard deviation. You also learned how to make visual representations, histograms, and the like. And then we transitioned into inferential statistics where we're testing a hypothesis. And we did this in a couple of different ways. You had about three or four weeks where we were looking at group comparisons with a one sample t-test, a paired samples t-test, an independent samples t-test, and even way back to the z-test. That's when we were comparing different groups. And then last week we talked about Pearson's R and correlation, looking at the relationship between two variables. So this is where we've come. And we've done all of our work so far on something called parametric measures. So backing up for just a minute, as a reminder, something I hope that you've learned in this class, a researcher's hypothesis can never be proven. If you hear people say prove, run away. We don't prove things with statistics. Statistics just helps us to make the best decision possible by assigning probability to our hypothesis statement. So how likely is the null hypothesis, for example? We've talked about low probability events or high probability events, and we've tried to distinguish between chance or systematic differences that are caused by the independent variable. Systematic just meaning there is a treatment effect. So that's what we've been working on. And we've talked about how significance testing provides a way to determine the difference between our sample and a population. So you've come very far. So we have two different types of test statistics. We have parametric tests and we have non-parametric tests. And parametric tests, which we've been doing up until this point, have certain requirements. So there's one assumption of all parametric tests is that the outcome variable or the dependent variable is either equal, interval, or ratio. So why is that important? Well, all the data analysis that we've done so far have relied on calculating a mean from a data set. Have you noticed that? They've all been mean dependent. We've been using the mean. And t-tests are basically comparing means of different populations, and a Pearson's correlation coefficient is computed through z-scores, which are converted from deviations between their scores and the mean. So we've been computing a mean all the time, and we know that to be able to find a mean, our variable needs to be equal, interval, or ratio. So we've been kind of stuck with this as our dependent variable. But means can't be calculated from ordinal or categorical or nominal variables. So that's what a parametric test is focused on, these equal, interval, or ratio data. We can't find, for example, the average of gender. We can't find the average of grade level. So we've been somewhat hampered in our ability to do all sorts of analyses. Our dependent variables have always had to be equal, interval, or ratio. Another assumption of the parametric test is that the outcome variable, the dependent variable, is normally distributed, or if it's not, the sample size is greater than 30. So what is the big deal about this bell-shaped curve? All the tests that we've learned so far have relations to the specific properties of a normal distribution, where the frequency distribution is a symmetric bell shape. That's how the math works. So these tests are called parametric because they're based on the parameters of a normal distribution. So think of that word, parameters, parametric. So we just need actually the sampling distribution, as we've talked about before, to be normal, not the original population. And in order to get that normal sampling distribution, we just need the sample size to be greater than 30. So the good news is always when the sample size is 30 or larger, the distribution of sample means is always normal. regardless of the population. But there are going to be times when you don't have a normal distribution and your sample size is small. And then what do? Do you just give up and go home? No, you do a non-parametric test. We're going to talk about that. So how can I tell if my data can be analyzed with the parametric test that we've been doing? So think about the following questions. Does the data set in front of you look like the Excel data sets in this course, where each row is a subject and each subject has a score that's a number? And if not, the data isn't appropriate for a parametric test. Does it make sense to take an average of the dependent variable? And if it's a numeric variable that's a ratio or equal interval scale, then yeah, you could find an average. But if not, it might be analyzed with non-parametric test. Do I have 30 or more subjects? If not, you can run your normality test with JASP or some other statistical software to see if the population is normally distributed. If not, you're going to consider a non-parametric test. So non-parametric tests help us when parametric tests fail us. So here's an example of a set of data that would be ripe for a non-parametric test. Who would you vote for if the election were held today? So this was actually a survey that was conducted, and it was conducted by NBC some years ago. And the sample size was 13,598 people, a lot of people. They were surveyed online. Candidate A had 55% of the votes, and candidate B had 42% of the votes. So what does this data look like? So this is just an example of what the data set would look like. So subject 1 voted for candidate A, and 2 for A, and 3 for B, and then you just simply do a count of those choices. So can we do a calculated mean? Can we find an average candidate A and an average candidate B? We can't, because these are nominal data. You can't find a mean. Is it a normal distribution? Well, not really, because it's just basically a bar graph. How many people chose A and how many people chose B? That's going to be two separate bars on the graph. It's not going to be normally distributed. Is it quantitative? Well, no, these are actually candidates' names, not names, but letters that represent candidates' names. They don't represent a number. I might change these to 1 and 2. I might code them as 1 and 2, but that doesn't mean that 1 and 2 mean anything mathematically. They're just categories. So what do you do? Well, you're going to do a non-parametric test. And in the next video, I'm going to show you the first kind of non-parametric test, something called the goodness of fit test. See you there.